Hello, everyone.
Hey, Scott.
How you doing, Mike?
Good, I'm doing well.
That's good to hear. It's been a while, been a couple weeks.
Couple weeks.
Yeah, and I think that I wanted to bite off a topic for Science Sunday today that I haven't really covered before, so treading new ground, as it were.
Yeah, this is out of your normal wheelhouse.
That's true. But before I do that, we have a guest with us today who needs to make an announcement.
Right.
Karen Campbell has an important message to share with our audience here at the DuPage Unitarian Church, as well as some of you online, regarding some current issues. So why don't you go ahead, Karen?
Thank you very much. This will be quick. I am a member of Citizens Climate Lobby, which some of you might know, and there's also a group in Naperville called the Naperville Environmental Task Force, and we are partnering with them and the First Congregational Church of Naperville to give Naperville voters a chance to find out what the environmental positions of the candidates are. And I thought that people in Science Sunday are probably interested in that. And this is Naperville, so I'm from Bolingbrook. I'm still doing it, though, because it's so important. Naperville is a big town, and what they do environmentally affects all of us. So I wanted to let you know that we have these candidate forums that we have organized, and there's one, and I have a little flyer. If you're interested, I'll leave these in the back, and you can take one so you can remember the date and the location. But they'll both be at the First Congregational Church of Naperville in downtown Naperville on March 8th, which is a Wednesday at 7. It's for the city council candidates, and I believe we have 10 who have replied to come. That might be all but one. And then the mayoral candidate on Monday, March 13th, also at 7 in the same place. And the candidates will be asked questions about how the Naperville city government can address environmental issues. For instance, this is a very topical question right now in Naperville, and this we have all their positions for those who have replied to our questionnaire. We put out questions in advance, so you could read some of these if you like on our website, which is on the flyer. And some of them, this one person has already replied to all the answers, and one of these questions is especially pertinent, not just to Naperville, but surrounding areas, because it affects the whole, area and state and the climate at large. Naperville's electricity supplier is among the dirtiest in the state of Illinois, with 70% of Naperville's electricity coming from coal power plants. That's Prairie State, it's called. Transitioning away from our current power supply is our highest impact action to reduce Naperville's carbon emissions, to curb global warming and attract businesses that have climate commitments. Would you support a resolution that commits Naperville to a responsible transition from coal to clean energy? And there are other questions. We have about 10, that not all of them are in that vein, but that's a pretty important one. So if you're interested in that kind of thing, and climate especially, it's nonpartisan. Please come to the forum and on March 8th and March 13th. Thanks. And
Thank you for doing that. That's great. We need that kind of involvement.
All right, thanks to the DuPage Unitarian Church for providing practical and enthusiastic emotional support. We've been doing this for more than a decade now, and we love Science Sunday, and we especially love you, and we love your participation. Last time during Science Sunday, we waxed a bit rhapsodic about how important you are to us, and having you in the audience is important. And so if you can make it in person, please consider being here. We have a nice turnout today. I'm getting motions from the audience that we need a little more volume in the sanctuary. So without further ado, I've got a lot of slides to get through today. It's a giant topic, geologic wonders of North America. Now, I start off with this picture of the globe. It may be a little different than the picture you're accustomed to. You've heard of Mercator projections and other kinds of map projections. Well, this is a projection that seems to mash all the continents together. If you look carefully there in the center, you can see the North American continent, you can see South America, some strange shapes of things that look like they might piece together to make Africa, etc. Well, this was Pangea. This is the way the continents were arranged many millions of years ago. The continents move around. I'm going to talk a little bit more about that later on this morning, about continental drift, as it were. But throughout Earth's history, the physical geology has been affected by the topology and the topography. Different continents coming together, different what are called tectonic plates merging and separating over time. And it's really caused a lot of interesting geologic phenomena. And we want to talk about many of them today with a particular focus on North American geology. All right. So as we go through today's discussion, it might be helpful to keep in mind some of this information about different time periods from a geologic perspective. So the Earth started about 4.5 billion years ago, and there was an era called the Hadean, where a lot of comets and asteroids and space junk, at the time it was junk, but it coalesced into a magma hot ball of material that we came to know and love as our clement planet Earth. And eventually
Can I stop you for a second? Dave, is there a way, it doesn't seem like the screen is getting
the slides.
Slides showing up on there. The slides, what's that?
All right. I'll keep talking then. So, much better? All right. And then we'll get the slides up there in just a second. So as soon as you'll see this slide, we talk about different eras. So the first one, the most ancient era of Earth is the Hadean. And during that period, Earth coalesced, and there was a collision between the baby Earth and an object known as Theia. Scientists have named it Theia, and that sloughed off a bunch of material from the mutual collision pair, and that material that was sloughed off became the moon. So the moon, for example, is made of material through and through that seems to be much more like Earth's crust than Earth's deeper regions of mantle and core. So the moon is sort of shaved off outer layers of the Earth. And that's probably very important for the eventual processes that we call plate tectonics today. And that all was because of physical and astrophysical processes that happened during the Hadean. And then that's followed by the Archean. Life arose. It was all single cell, simple, what we would consider simple life. And then the Proterozoic, where you get to have all kinds of geologic changes with the Earth. Snowball Earth comes and goes. I'm not going to talk much about that today. And then beginning about 540 million years ago, we had the so-called Cambrian explosion and what's called the Phanerozoic. So that's the era of complex life, and life began to live on the land as well. Prior to that, life was limited mostly to oceans. Now, one of the things we can do is we can take that Phanerozoic, the last 540 million years, and we expand that into different geologic periods. So you've heard about some of these, the Cambrian, the Ordovician, the Silurian, the Devonian, the Carboniferous, et cetera, and some of those words will be used throughout this talk, but I'm going to try and avoid a lot of these technical terms because many of you probably, and myself included, I don't have this map of time burned into my memory. So we're just going to talk about terms like millions of years ago, or thousands of years ago, or billions of years ago. So 1,000 years ago means Ka. 1 Ka is 1,000 years ago. K is for kilo, 1,000. 1 Ma is 1 million years ago. 50 Ma is 50 million years ago. And then 2GA means 2 billion, G for giga, like a gigabyte, 2 billion years ago. So that terminology will be used throughout today's talk. All right. What I plan on doing is going through time in terms of the content that I'm covering for today. Let's start about 540 million years ago at the beginning of the Phanerozoic. And we're going to talk about some of the topography that came together at that point to form what's called the North American Craton. It's also sometimes called Laurentia. And that's the sort of brown splotch there on that map on the left. Now, if you look at the map on the right, that shows various what are called geologic terrain. Now, that's different than what you typically would write or refer to when you're saying something like it's got an undulating terrain, or the terrain around here is very hilly, etc. This is actually spelled differently, and a terrain is, in this context, a contiguous piece of geologic material. So it could be an arc of islands, it could be a volcanic region, it could be a sedimentary basin. Each of these forms its own terrain. And the map on the right shows different terrains that came together to form the North American Craton. And you see names there like Superior and Churchill, etc. Well, those terrains came together to form much of the core of North America, much of the core material of North America, billions of years ago. And they have stuck together largely ever since, quite literally. And it forms what is known as the North American Craton. That material constitutes some of the oldest material on Earth that has not been subsequently subducted or driven down into the Earth's mantle and remelted. So there's still material there that is, in many cases, billions of years old. It's kind of hard to see there in that rightmost graph, the map, but starting at the top, the blue area is the Phanerozoic age, so that's 540 million years or younger. And then all the way to the bottom where you get that kind of flesh-colored pinkish orange or peach color, and that's Archean. So that's stuff that is 2 billion years or more years in age. And if you want to find the oldest rocks in North America, you've got to go to either a spot in Minnesota that I'm talking about, or the very oldest known, some of the oldest known rocks on Earth that are exposed at the surface is right here around Hudson Bay in Canada. And that material is about 2 billion years old. You can pick up a rock and hold it in your hand, and that rock consolidated from lava about 2 billion years ago. Pretty amazing. However, if you want to, some of you will probably be curious about what is the oldest Earth rock ever found. And I'm not talking about fragmentary microscopic crystals. I'm talking about the oldest Earth rock. Well, the oldest Earth rock known to date actually comes from the moon. Now, remember I said the moon was created from materials sloughed off from the Earth. Well, that's not what I'm talking about right now. What I'm talking about right now is that a large impactor hit the Earth subsequent to the formation of the moon, and it blasted off so much material so vigorously that you get rocks of Earth scattered on the moon. Shrapnel from the Earth that ended up on the moon. And the Apollo 16 mission found a Earth rock, and they can tell this because of looking at radioactive isotopes and chemical abundances to see whether this particular rock was native to the young Earth or not. And what they found was a rock that comes from the Earth, but dates to 4.46 billion years ago. And the astronauts picked that up and brought it back to Earth on Apollo 16. So here's a nice picture of Earth as seen from the orbiting capsule. And I think that's from the lunar lander actually ascending back up to meet with the command module. Anyway, this is a picture of that rock. This is the oldest known rock that humans have ever discovered. And it's 4.46 billion years old. And that's in a collection here on Earth. And it's a few inches big.
You'd have thought it had been dusted over or pounded by subsequent asteroids or...
Yeah, there are
coming through.
micrometeoroid impacts that have been measured on this rock, and so they can use some of that evidence to piece together how long it's been sitting on the surface of the moon versus how long it had been on Earth and whatnot. So lots of science can be dug out from looking at the pitting and chemical composition and isotopic composition of that one rock. So I want to move on. So as I said, this is kind of a time journey. We're going, that was 4.46 billion years ago. Now we're at about 2 billion to 1.2 billion years ago. And one of the interesting things that happened in North America specifically is that our continent, for reasons that are somewhat mysterious, I talked about geologic mysteries, our continent started to rip apart. And the scars of those rips are filled by water today, and we call them the Great Lakes. So many of the Great Lakes, Superior and Michigan and Huron, I think, are largely the result of some filled fractures in the earth. Like you've heard of the Great Rift Valley in Africa? Well, the United States had its own Rift Valley about 2.5 billion years ago, where the North American continent started to tear apart, and then it stopped. And the rift, over time, filled with sediment, and there were shallow seas that came and went and deposited layers of material that accumulate in oceans, like a lot of carbonaceous materials, limestones and dolomites and whatnot. And in any case, the remnants of this about 2.5 billion year old tear in the continent of North America still leaves a visible footprint on our continent now, particularly along the shores of Lake Superior. The north shore of Lake Superior contains rocks that are about 2.7 billion years old. It's old volcanic rock that is accumulated there on the north shore as part of the that fissure that opened up in the continent as it began to tear apart. And you'll notice that some of that fissure, geologists use magnetic scientific instruments that detect the magnetism of rocks buried in earth to trace out some of these fissures, and then some of them subsequently filled with later lava flows. And much of the lava that can come out of a volcano is highly susceptible to orienting with regards to Earth's magnetic field and being frozen in place. So they can look at the magnetic orientation of material buried underneath the top of the Earth. They can scan down into the Earth and figure out these where these different channels and flows of lava and whatnot, where they lie under today's topography. And this is in brown and green here. Brown is what are called clastic sediments, so that's volcanic pumice and other lighter materials that are suspended in water or air that come from volcanoes. And then the dark green on this map are igneous rocks, so that's where the lava flows were there during that rift. Now, I talked about the African rift, the Great Rift Valley. One of the things you'll notice that's common between this image and the prior image is this kind of Y shape. So this is a classic feature that shows up again and again in plate tectonics and the studies of the way plates move and come together and tear apart over time. If I go back here, you'll see that kind of Y shape that I've highlighted there with the blue arrows. And then here in the Great Rift Valley, you'll also see kind of a Y shape. That triangular pattern for rifting is common and is a feature that geologists look for when they're trying to piece together the way the pieces of the Earth moved over ancient trajectories. All right. I talked about, momentarily, I talked about some of the oldest rocks you can find in North America are up in Canada, but there's also some really, really old rock in Minnesota. And this is called the Morton gneiss. It's spelled G-N-E-I-S-S, but it is pronounced gneiss. And this Morton gneiss is named after the town of Morton, which is in southern Minnesota. And this rock is about 3.5 billion years old. You can drive down this road, pull over, and put your hand on rock that is 3.5 billion years old. Isn't that mind-blowing? Just the idea that the Earth is that old was relatively a recent piece of scientific insight on the part of the human race. As recently as the time of Charles Darwin, in the mid to late 1800s, there was speculation that the Earth might be, 100 million years old, or a couple 100 million years old.
Well, I think the big debate was Lord Kelvin,
That's right.
famous physicist of the time, and he was looking at how the Earth was losing heat as time went by, and by that calculation, he came back, and I think he was talking about only a few 100,000 years old. And he was such a well-respected physicist that it put a lot of people
Right.
Unwilling to accept Darwin's views, because the evolution that Darwin was looking for, development of diversity, couldn't have occurred in such
Right.
a short amount of time.
Yeah, I'll put a plug for my book, which Bob is hopefully providing me some feedback on some typos I have and whatnot. I hope to have the next edition of my book out later this spring. But one of the things I talk about there is something called the anthropic principle, which is the notion that the universe is amenable to human life. And there's a prediction that could be ascribed to the anthropic principle, a predictive power to say, we're here, therefore certain things must be true about the universe. Well, Charles Darwin kind of did that in terms of his line of reasoning and say, well, we're here, and horses are here, and finches are here, and in order for them to be here in the form that we see, they must have had millions of years of gradual evolution. And that kind of flew in the face of conventional wisdom at the time, which was that the Earth was anywhere from a few thousand to maybe 100 million years old. And Darwin said, no, we need a lot more time than that. And Darwin actually considered himself a bit of a geologist, but he was right at the cusp where the science of geology was developing, and they were beginning to think about the ice sheets and the glacial periods of the Earth and whatnot, and he was familiar with some of those nascent studies. But that was really a transformative time in our knowledge, not just of life on Earth, but the history of Earth itself back in the late 1800s.
1830 or so, Charles Lyell came out with Principles of Geology,
Right.
which basically was the first assertion that things are happening at a slow, gradual rate now, and that implies that things always happen at a slow, gradual
Right.
rate. There wasn't this cataclysmic type of development of the Earth and cataclysmic floods and cataclysmic creation of different things.
Right.
So that started pushing back against kind of the 6,000-year-old version of the
Right.
creation of Earth.
Right. So amazing stuff. And we're so lucky to be alive at a time when all of us have access to this amazing knowledge about where we come from, where our planet comes from the generation of its elements in the heart of stars, to the coalescing from a pre-solar nebula, to the plate tectonics that have reshaped the continents over aeons. and some of the forces that reshape rock. So this gneiss kind of rock, G-N-E-I-S-S, this gneiss rock, it's metamorphic. So it's transformed by heat and pressure. And all that heat and pressure, one of the things it causes is for the minerals in the precursor rock to differentiate into layers and bands. These layers tend to be horizontally deposited with respect to the local gradient of gravity. And so if you look closely at this rock, you'll see all these colorful bands in it. And that banding over 3.5 billion years has been morphed and warped. So rock, over billions of years or even millions of years, rock is relatively plastic. It can be slowly bent, very slowly bent, if you put enough pressure and heat into it. And over time, all those bends, by the way, this is where the town of Morton is there in Wisconsin. And we're going to come back and visit something interesting about this town in a minute. Or not Wisconsin, in Minnesota. Well, this wonderful Morton gneiss is a preferred building material. So the Adler Planetarium, downtown Chicago, has a facade that is made from this Morton gneiss. And I don't know if you can see well on this, but you can see all those warped, colorful bands in it. It's a beautiful, beautiful rock. And all those warping and twisted banding is because of the plasticity of that rock over geologic time, 3.5 billion years. So anytime you visit the Adler Planetarium downtown, you can put your hand on rock that was coalesced and solidified 3.5 billion years ago. You don't have to go all the way to Minnesota. All right. So here again is a picture of Pangaea, and you'll notice that there's this line that your presenter has helpfully drawn here to separate North America from Africa. And at some point, about 330, should say million years ago, not billion years ago. That's my error. Both of those headers should say 335 mega years ago and 200 mega years ago. I apologize for that. In any case, at some point, about 300 to 200 million years ago, the east coast of the United States and the north coast of Africa were in contact, right? And these were tectonic plates that were rubbing against each other, and anytime you have that happening, the tectonic plates themselves, the cratons over which the crustal material is deposited, the crust of the earth, the stuff we see around us, like, I don't know, granite and limestone, that's really fluffy. That's really light and fluffy stuff. I don't know if you've ever hit a piece of granite. It's really fluffy. And it floats on top of this much denser magma-derived material that contains a lot of iron and magnesium and a lot of literally heavier elements. So all this crustal, fluffy stuff floats around on top, and it tends to mush together over time. And what happens when you mush fluffy things together? Sometimes they warp and bend and pile up. Well, in this particular pile up, some mountains were generated. In geology, they have one of my favorite words. Whenever a geologist talks about the building of mountains, they'll talk about an erogenous era. And they talk about erogenous zones, right? Talk about exciting, right? It just doesn't get much better than that. So during this Pangaean orogeny, it's an OR, right? Just for those of you who might have been thinking something else. During this era, the mountains that we today call the Appalachian Mountains were generated because of this mashup between this light, fluffy crustal material and some of the stuff in Africa, and strangely enough, some of the rains in Europe. Now here's a little bit some of the facts about the implication of the geology and the topography at that time. About 300 million to 200 million years ago, this continent and that blue, red line that you saw was close to the equator of the Earth. So it got a lot of equatorial rains and whatnot, but that newly forming mountain range caused a rain shadow, so you'd get salt flats in Europe. And over the subsequent 200 million years or so, those salt flats in what is today northern Europe were a dry sea, shallow sea, and the water evaporated and left behind salt. So there's a lot of salt mining in Europe, and those salt flats are a result of the rain shadow cast by the Appalachian Mountains at that time. Really amazing stuff, how it all just sort of comes together and makes this wonderful narrative about how the world got to be the way it is.
Comes together, but then again, it
But
comes
then
apart.
breaks apart again, yeah. Yeah, it's all short-term relationships in geology.
Oh, what's a few million years among friends?
That's true. You find another, you know, it's all, the continent's always greener on the other side of the ocean, I guess. Oh, no. Uh-oh. Shoot. I accidentally tapped the microphone.
Up towards the top.
Oh, shoot. I just tapped it with my thumb. Hello, hello. Testing, testing, testing. We got it? Is it back? Hello?
Cut your thumbs off.
Hello? We're back? All right, can you put the audio up a little bit in the sanctuary? I get so excited. I mean, what's not to love about geology? This is really cool stuff. Anyway, I'll try not to speak with my hands so much. I'll put them back behind me. So here's a picture of Gondwana was one of the continents that came together to form Pangaea, and you've got another continental mass called Laurentia. Remember I said that the North American craton, one of its names was Laurentia? So that's North America there. If you look really carefully, you can see an outline of West Virginia. So West Virginia is our oldest state, dating back about 300 million years. I'm kidding, right? It's actually one of the newer ones. It was made during the Civil War. They didn't want to join the ruckus on part of the South. But in any case, you see these mountains, this mountain chain. Then yellow is the Appalachian Mountains. And then in red are the Atlas Mountains. And they were all part of the same erogenous event. Surprisingly, so are the Scottish Highlands. So the Scottish Highlands, the Atlas Mountains in Africa, and the Appalachian Mountains in North America were all part of the same mountain chain when they were formed. And they broke apart. And they are some of the oldest mountains on Earth. At one point, it is likely that they towered similarly to the Himalayas and have since been worn down over the course of millions of years. And here's another picture sort of highlighting the extent of the mountains that arose from that collision between 400 and 200 million years ago. But the rocks that form these mountains, right, it was crunched up, fluffy rock. That rock itself was about 1.2 billion years old. So that rock was folded up into mountains over time. All right, next, we're going to talk about, we're going to go to a different place in North America. We're going to go further south, and we're going to talk about the Chicxulub crater that resulted from the asteroid impact that has been implicated in the demise of dinosaurs, except for birds. Birds are dinosaurs that survived, as I'm sure you know. So here is a nice, pretty animation of the asteroid hitting the Earth, causing tsunamis and atmospheric disruptions and a wave of hot plasma that started forest fires throughout North America. And you'll see there also some maps of the way North America looked back then. That's the map on top. And the map on bottom, and then it's got a little bullseye there on the map on the bottom that shows where the asteroid struck. It struck in a shallow sea, and it struck into some mineral deposits there that were particularly nasty to be thrown up into the air. So it hit at one of the worst possible spots. Of all the places it could have hit on the planet Earth, it hit at one of the worst spots in terms of disrupting the atmosphere and the oceans. And that crater, the Chicxulub crater, the remnants of it still persist to this day. It's there on the Yucatan Peninsula in Mexico, and you can trace a circle of where the crater was based upon where the impact occurred. It occurred actually a little bit what would today be offshore, was where the center of the impact was. But interestingly enough, when a heavy object from space hits our planet, it creates ring-like fracture network around it. Think of a bullet hitting glass and the safety glass and the rings that come out from it, or throwing a pebble in the pond and the rings of energy that spread out from the point of impact. Well, similarly, there were rings that spread out from the point of impact of this asteroid from 65 million years ago. And the fractures in the rock in the Yucatan Peninsula are still relevant today. Those fractures have been filled with rainwater over time, and rainwater dissolves more of the rock and whatnot, and these form little sinkholes or caves called cenotes. And these cenotes are a unique ecosystem in Mexico, and some of the plant and animal life in these cenotes is unique to the cenotes. And these unique habitats that are beautiful places, some of them are actually equipped with boardwalks and whatnot. People go down and swim in mineral waters and whatnot. These cenotes are the direct result of the asteroid impact 65 million years ago. So with every catastrophe, there are new opportunities for life and geology to branch off into new directions and create interesting new formations and forms of life. Now I'm going to jump way back up north again. Now here's something that looks like it might be a circular crater. It's about 450 kilometers in diameter. You see there in the middle there's some peaks in the form of islands. This is up in Hudson Bay in Canada. And you see this almost perfect circle here, this bite taken out of part of Canada. Well, that looks a lot like a crater, but it isn't. So in the 1970s, an expedition went up there to say, well, let's go see what this crater is all about. And they tried to find shock cones and shocked quartz and other evidence of an impactor, and what they found was a whole bunch of nothing. Nothing special at all about the geology around this bite taken out of Canada. So this is another geologic mystery. How did we form a nearly perfect part of a circle through geologic processes? And there's speculations about it. Maybe it was due to subducting plates or colliding plates in the distant past, or maybe it's the echo of an impact crater that is so ancient that all the rocks available to us to study lack any signs of the impact itself. The jury is still out. There's still science to be done to figure out some even giant features on Earth like this. All right, moving south again, whirlwind tour of North American geology. We've got this thing. I assume you know what this is, right? The Grand Canyon. The Grand Canyon was largely carved by the Colorado River that flowed along the Colorado Plateau. Now, at the time, there was the Rocky Mountain orogeny, when the Rocky Mountains and all along the Pacific Rim there were being uplifted by tectonic forces. There was a part of the Colorado Plateau that remained largely intact and flat. And what it did was it tilted north to south a bit. And nobody knows for sure why. Why did it remain intact and why did it tilt?
And it rose up almost 3,000 feet or something like that as well.
Yeah, nearly a mile into, it lifted up and tilted and remained flat. And meanwhile, this river, the Colorado River, started finding its way through it. And the Grand Canyon exposes rocks that are billions of years old down at the bottom, about 2 billion years old. So how long did it take the Grand Canyon to be carved? Well, here's a little bit of math for you. I did it, you don't have to. If you have a river that's cutting off 1 millimeter a year from the bed of the river, 1 millimeter a year, well, how much does it cut in a million years? 2 kilometers. I asked the Amazon Echo device in my home to do the math for me, just to make sure I hadn't made an error. I said, what is 2 millimeters times a million? And the answer was 2 kilometers. So a little stream that only eats or chews out a millimeter a year, or let's say 2 millimeters a year, can carve something a half mile deep in a million years. So the Grand Canyon could have been a mile deep in only 2 million years. And in fact, that's what they think, is that the canyon itself, not the rocks on the walls, but the canyon itself, is about 2 million years old. Relatively new feature in the history of geology.
The interesting things, I think the top layers at the Grand Canyon are what the bottom layers are in Zion, which is north of there by 300 miles, maybe something like that. So it's got this tilt up to it. And so each of those places you can go and see a whole different slice of the life on Earth, of the geologic life of North America, going back over 2 billion years.
Yeah.
And you can see it all in a progression.
Yeah, you can drive along the surface of the Earth, and because a lot of those layers have been tilted, you can drive along the surface and go forward or backward in time, depending upon how you point your car. Not literally forward and back, because that would be really awesome in other ways. But
you have to have what kind of?
Like super relativistic
Lamborghini?
engine. Yeah. So really, really awesome stuff. Let's see. Continents move about 2.5 centimeters a year. So we're not talking a millimeter a year. We're talking 2.5 centimeters a year. That means in a million years, a continent can move 25 kilometers.
You're talking about the spreading away.
Yeah, the moving of continents themselves. Mm-hmm. And the fastest continent on Earth is blazing at about 2 inches a year. So it's about twice as fast, about 5 centimeters a year. And that means that in 50 million years, something moving an inch a year can move 1,200 kilometers. So that means something moving at 2 inches a year could move 2,000 kilometers in 50 million years.
They say that it's separating, that the movement of the plates is about equivalent to the speed that your fingernails grow.
Right,
Yeah.
right.
The way to think
So
about
that's
it.
part of this deep time idea, like a little river rumbling its way or roiling its way across a flat plain. No big deal. You give it a couple million years and it makes the Grand Canyon. You get a continent that's moving at the speed of a fingernail. Okay, not very exciting. You give it 50 million years and it's halfway across the world, right? So that's some of what happens in geology that requires this concept of deep time. So it's not just biology that is changed by the progress of the eons. The Grand Canyon, the western end, the very western end of it may be something like 70 million years old. There might be some fissures there and some streams there that began carving about 70 million years ago. The majority of it, however, was carved in the past 2 million years. And again, during the building of the Rocky Mountains, which is called the Laramide orogeny, during that, why did the Colorado Plateau remain nearly flat? Why did it tilt? Why did it uplift? And then the final question is, what about the Great Unconformity? Have you heard about the Great Unconformity? No? All right. So if you pay attention to people who like to argue from a strict biblical perspective, they will tell you about the Great Unconformity, and they will point to the Grand Canyon as evidence of it. And they will say that this is a big geologic mystery that can't be explained by science, where you've got this rock that's about 2 billion years old, and then you've got rock that's about 500 million years old, and where's the gap, right? Well, anytime you have a gap in the geologic sequence like that, it's called an unconformity. And a gap of 1 billion years, which is what this gap constitutes, is called the Great Unconformity. And there is evidence for this great unconformity in the Grand Canyon and in other places in America. So here's a column that shows the geologic strata available to scientists in a lot of the desert Southwest region, including the Grand Canyon. The black area, so the black, mostly black strip there in the middle of the slide is time, going from ancient down at the bottom at about 1.9 or 2 billion years ago, up to the top. And the black areas in here represent time that is missing from the geologic era. On the far left side of this slide, you'll see a graphical diagram of the different strata available in the Grand Canyon. So here you see part of that tilt, where the blue area from about 0.7 billion years ago, called the Char group, how it's tilted and incorporated there. I don't have time to go through this in great detail, but I will tell you the high points, such as erosion happens. And one of the other things that happens is shallow seas can come in and deposit material that turns into geologic strata over time. But if there's no sea, if there's no water, there's no deposition of new material. So you don't get new land being built on top of old land. Instead, you have it eroding away. The other thing you can have are glaciers. And depending upon where this part of the continent existed millions of years ago relative to the poles of the Earth or the equator of the Earth, you can have different climates and you can have glaciation. Not to mention the fact that at least twice in Earth's history there was what's called the snowball Earth phenomena, where most, perhaps nearly all, of the Earth was covered by glaciers. And those glaciers, just like glaciers in our recent past, would have scoured the land and swept away, plowed away a lot of material. So unconformities in the geologic record have a perfectly rational, naturalistic answer that don't involve things like the Great Worldwide Flood or magic. It's indeed just geologic processes. All right. Another thing that's really interesting in the southwest part of the United States is, and the northwest part of the United States, is Yellowstone. Yellowstone started down in Nevada and worked its way up into Montana over the past 16 million years or so, the hot spot. There's some debate about whether the hot spot of a plume of hot material coming up from towards the center of the Earth, whether that magmatic plume has shifted or whether this is purely due to the drifting of the North American continent over that hot spot. Probably a combination. Anytime you see scientists arguing about one or the other, many times that ends up being resolved by a compromise of nature taking a little bit of both phenomena into account. So about 16 million years ago, the hot spot was down on the border of Oregon and Nevada, and today the Yellowstone caldera is what it's called, is in Yellowstone National Park. And about 640,000 years ago, the Yellowstone caldera erupted in what's called a supervolcano, not necessarily by geologists, but in the popular press, it's called a supervolcano. Before 640,000 years ago, it erupted about 1.3 million years ago, and before that, about 2.1 million years ago. And there's currently debate about whether it's literally cooling off and unlikely to erupt again, or whether we have another Titanic scale eruption of the Yellowstone caldera in our distant future, which would be pretty bad because it would coat most of North America in volcanic pumice, as has happened in the past from this hot spot. And you see also on this some lava flows associated with what are called the Columbia River basalts. Basalts are that heavy lava containing a lot of magnesium and iron, and they came from the mountainous region as represented there on the map, a lot of basaltic material. One of the reasons all of this happens is because as plates come and disjoin over time, as they smash together and move apart, some of the crustal material that rides on top, some of the fluffy bits, gets subducted down into the earth, and they melt, and because they're lighter, but now they're hot, lighter weight stuff rises, and you get volcanic plumes and mountain building. Not because of the folding of the earth, but because of volcanism. You get these giant shield volcanoes, like in the Cascades of the Pacific Northwest, and Mount Fuji in Hawaii, and the volcanoes of Japan. Mount Fuji in Japan, and the volcanoes of Hawaii, where the hot spots, these magmatic plumes under the earth, usually from relatively lighter material that squirts up from the surface onto the surface. That's also a way to build mountains. But the ancient crust, ancient pieces of ancient cratons or ancient crustal material can move thousands of miles underground, as it were, over millions of years. And there's a subducted plate that is believed to exist under North America. And that's the light green region there on the map, showing that subducting down underneath Middle America. And we're going to talk more about that in just a minute as about our final topic, close to our final topic. And so I wanted to talk a little bit about the Mississippi. I'm cognizant of time here. I've still got about 10 slides to get through. The Mississippi is about 2 million years old also, interestingly enough, about the same age as the Grand Canyon, although there are parts of it similar to the Grand Canyon that are about 70 million years old. Its current course and its extent is relatively recent in their geologic record. Here's an interesting fact. The Mississippi River is the longest continuously navigable river in the world. It's amazing. This is one of the reasons America is such a prosperous country, is because our very fertile heartland has been for centuries able to move its goods down a navigable river. If you look at other rivers like the Nile, other long rivers, some of the rivers that originate in the Himalayan mountains, they have a huge gradient as they move towards sea level. And so they have cascades and waterfalls. Well, you can get in a barge or a boat, and you can, other than man-made obstructions typically, you could go all the way from New Orleans up to the Twin Cities of Minneapolis and beyond on a river that didn't try to fight back too hard and didn't have any cascades. And that's unique in the world, a unique piece of river-related geology. This is the drainage basin of the Mississippi and its tributaries. And then here's another map showing the fertility of farmland in America. And you'll notice a little bit of a correlation here. So the Mississippi River is a geologic wonder that has enabled the prosperity and feeding of America. Next, this is a picture of Los Angeles from about 1901. And those are oil derricks in the background. So there's a big oil field under Los Angeles, largely depleted now. And then there's some men down there digging a hole. Why would they be digging for oil when you could just drill for it? Well, they're not digging for oil. This is actually the La Brea tar pits back at the turn of the century. And it's not actually tar, it's asphalt. Chemists, and especially petroleum engineers in the audience will know about that difference. Here's a picture of today, some skyscrapers in the background, and some mastodons frolicking in the warm waters that overlie some of these tar seep or asphalt seeps. Of course, these are just statues. The real beasties are unfortunately gone for the past 10,000 years or so. But they were there, and many of their bones, and direwolf bones, and saber-toothed tigers are all there. And talking about recent geologic history, is it okay with everybody if I go over by like 5 or 10 minutes? Anybody have a... All right, good. So talk about, now we've gone ancient, 70 million years, 4 billion years, now we're up to just a few thousand years ago, 30,000 years ago or so. Big ice sheets. Apparently the mammoths were not particularly impressed, but I would have been, right? These things were taller than skyscrapers, a wall of ice, just amazing. And these walls of ice were in motion. So here's a picture of where those ice fronts got to as they were sloshing around on the surface of the earth. The light, the sort of the light gray is the north, where there was all ice, so you can think of that as being almost white. Up in Minnesota and upper peninsula of Michigan and lower peninsula of Michigan and whatnot, that's ice. And then you see these ice fronts. So that's the really dark gray area was a very early glaciation from about 50,000 years ago, and then the sort of intermediate gray there in much of Illinois is called the Illinois glaciation. The lighter gray stuff that is mostly up in Minnesota and Wisconsin and half of Illinois, the lighter gray stuff was part of the Wisconsin glaciation. So the Wisconsin glaciation and the Illinois glaciation. The fact that geologists bothered to give them those names gives us a hint that there's a lot of glacial features in Illinois and Wisconsin from two different glaciation periods, separated by tens of thousands of years in time. There's the Illinois glaciation period and the Wisconsin glaciation period. And the Wisconsin was the most recent. It ended about 10,000 years ago. So here's another interesting map. It shows some of the topographic features left behind by the ice sheets. These are what are called terminal or end moraines. So a moraine, think about a bulldozer. You got a bulldozer coming along, and if its blade is lowered, it's just scraping the dirt in front of it. And then when the bulldozer stops, it leaves a little ridge of dirt, right? Well, the glaciers did something similar. They scraped dirt, but they were also carrying a lot of material inside them, and they dumped that material on the ground when they melted, and they left what are called terminal moraines, or these little hills that you can very literally trace out the edge of where a glacier was 10,000 years ago by following a hill, following a glacial moraine. And you see these moraines represented here in all over Michigan and Iowa and Illinois. Pretty amazing, amazing stuff. And during the glaciation periods of North America, one of the things that happened as the ice melted was that it created ice dams, these 2,000-foot walls of ice that prevented meltwater from the glaciers and other water from rain, etc., prevented that water from moving into where the glacier resided. The glaciers formed literally an ice dam. And there was this glacial Lake Missoula in the Pacific Northwest that formed a lake as big as a Great Lake, as a modern Great Lake. And when the ice dam melted and eventually gave way, car-sized boulders were moved as much as 500 miles. Imagine a boulder bigger than the span of your arms being thrown by the current 500 miles away. Tremendous flows of water when these ice dams broke. And by the way, speaking of the Bible, there's some scholars who think that similar phenomena in some of the cradles of civilization 10,000 years ago or so were imprinted on mythic stories that were passed down from generations about catastrophic floods coincident with the end of the last ice age that would have changed the landscape and been devastating for low-lying areas. Here's something called a glacial lake. This is Lake Palcacoca in Peru. You see there are these plastic pipes going into it. They use it as a water source. There's a man or a woman, I can't tell. There's a human being camping out there with some tents. So this is a glacial lake. The glaciers coming down from those distant Andes mountains melts and provides all this fresh water, which is quite helpful to the people who drink water. Well, here's another picture of a glacial lake, a schematic representation of one. This is called Glacial Lake Agassiz, and it was up north of Minnesota, largely into Canada. The Great Slave Lake is a remnant of this, and you see it is vastly larger than the combined area of today's Great Lakes. And this existed about 10,000 years ago, 15,000 years ago. It also broke through its ice dams eventually, and racing through this, here's the extent of the ice caps. I don't know why they're black on this picture rather than white, but these are the ice caps in the northern hemisphere during the Wisconsin glaciation. It's got to be later than that, or earlier than that, because it extends down into Illinois and Iowa. But in any case, there's Lake Agassiz on the left-hand side, and you can see it extending down into Minnesota, halfway down or more the length of the state of Minnesota. And here's another picture of it, a little easier to see. And one of the things you'll notice is that the very tip, the southern tip of Lake Agassiz meets up with the channel of a river. And that river is called the Warren River. Back in Paleolithic times, when 10,000 years ago or so, it's called Glacial River Warren. And when the ice dam broke and the water flowed out, it carved out a valley that was tremendously large. So here's the current Minnesota River. It's the little blue speck down there on that profile, the relief profile on the bottom, the little blue line right on the right-hand edge. That's about, I don't know, 100 yards across or so. That's current Minnesota River. But Glacial River Warren, that burst from the ice dam at the end of the last ice age, was so vigorous that it carved out a channel a mile wide and about 250 foot deep. And by the way, that happened, the most significant carving out of the land there happened right there by Morton, Minnesota. So fortuitously, when it carved out the land, it exposed some of that Morton gneiss that we mine today for building facades. One of the things that happens during these events is you get sort of aquamarine tornadoes, these vortices of swirling water that are really powerful. And just like some of you sometimes see under waterfalls or where waterfalls once were, these little tiny holes where a pebble gets caught in the current and it carves out these little kettles in the bedrock or in the rock under the waterfall. Well, imagine that happening with a car-sized boulder with those, some of those, they're called colks, these underwater vortices. They're like an underwater tornado. The Laurentide ice sheet that caused all of this ruckus in North America has now shrunk, thankfully, uncovering a lot of farmland in Iowa, Illinois, Minnesota, etc. It has now shrunk to the point where there it is. That's the remnants of the last great ice sheet that covered North America. The Laurentide ice sheet is right there on Baffin Island in northern Canada. And it's melting. It probably won't be there in another century or two. All right, here's the lobes of the glacier. You'll notice that there's a suture between the what's called the Green Bay lobe and the Lake Michigan lobe. There's a thing called the Niagara Escarpment that curves around from the Green Bay Peninsula of Wisconsin, curves up through the Great Lakes and down to Niagara Falls. It's a really hard cap rock that's found throughout the region. And when the ice came during the glacial periods, that cap rock also kind of guided two different glacial lobes. But because there were two lobes that met there, they also left a bunch of debris behind. So there's a lot of moraines. Remember the debris carved up by glaciers? So you can look at a topographic map of Wisconsin and literally see where these lobes were. I mean, here on this map on the left, you can see just clearly where the ice went because of the debris it left behind. And here's a highlight of some of that debris. There's some wonderful geologic trips you can take up in Wisconsin, self-guided or otherwise, to explore kettle moraines and kames and other kinds of phenomena related to the ice sheets. Another wonderful piece of topography related to ice, you get these long, sinuous lines of they're in ice rivers, so rivers that flowed within the ice or under the ice, and they were loaded with sediment, so they leave behind these ridges that you can also see. New York City once had glaciers covering it, and if you look at Long Island, you can see that Long Island, a lot of Long Island is a glacial moraine that's left behind. Final topic for today. In 2008, I believe, there was an earthquake in Illinois. That was probably all of you who lived here at the time. It was about 4:30 in the morning, and it's a result of some tectonic forces that are active in what's called the New Madrid Fault and the Wabash Valley Seismic Zone, two seismic zones. So I told you about the continent ripping apart 1.5 billion years ago. Apparently, it tried to do it again about 700 million years ago, only this time the rip happened about where Missouri and Kentucky and Arkansas come together, and Illinois. So it was a smaller scale event. We don't have any Great Lakes there, but it is the path of the current Mississippi, and some of that subducted material from the collision of the plates billion years ago or so have created some seismic instabilities underneath the center of our nation. So here's some information about that earthquake. And it was about 4:30 in the morning. I remember waking up to it thinking that a truck, I live in a quiet suburb, and there would be no reason for a truck to be driving around on my streets, but I thought a truck had jumped the curb outside my house. But it was just the jolt of an earthquake. And if you look at this USGS map of earthquake risk, the places in red are the places in the United States most at risk of having an earthquake over the next 50 years. They say that over the next 50 years, there's a 10% chance in the red areas. So equivalent to California down in New Madrid area. That's it. I wanted to tell you that you can purchase online, not associated with me in any way, but these beautiful topographic colored maps. You can get them on Pinterest. A couple of different versions of the map of Illinois, clearly showing the orangish area. On the one on the left shows clearly where the glaciers went during some of the glaciation periods. Beautiful geologic maps. You can get these for nearly any, these kind of maps for nearly any state. Some of the books I use, this is Annals of the Former World by John McPhee. John McPhee is one of my favorite writers. He's a science and natural history writer. He combines stories about human culture and human interest with science. He's written many books. He's a Pulitzer Prize winner. In fact, this book won the Pulitzer Prize. This was the first book I read about geology 20 years ago or so. Annals of the Former World by John McPhee. And then I also have in my library Field Guide to Geology. So there's lots of fun textbooks available. And then nearly every state, I haven't checked 50 times on Amazon, but nearly every state has a book like this. This is Minnesota Geology. You can get Michigan Geology. I have that one. I have Wisconsin Geology. I don't yet have a book just on Illinois Geology. I don't know. I'm bad that way.
It would
But
be a pamphlet, maybe more.
yeah, probably a two-pager. Anyway, full of history and geology of the state of Minnesota as well as surrounding regions, because Minnesota was affected by the Wisconsin and Illinois ice sheets, so they talk about that. Anyway, a wealth of resources, a wonderful, very deep topic, if you will. Thank you so much for joining us for Science Sunday this time. And I guess I'm willing to stick around for any questions or comments if anybody has any. Sorry for running a little bit over. Thank you.
There I was in the 1950s, which is ancient history to many, but in this group it's just yesterday, looking at the silly map of the world and noting that South America fits right in. South America and Africa should be the same thing. And then you look at North America, just turn it just a little bit, it's the African coast. And so I said to my teacher, weren't they all connected at one time? And she says, oh no, this is how the world was made.
That's just an illusion, they would say.
Yes, it's just an illusion, it just
looks like
happens
that,
to
yeah.
be.
Coincidence.
A quinky dink.
Yeah.
And of course it was 10 years later that everyone's going, wait a minute, wait just a second, let's look at the oceans. And
You were asking exactly the right question and proposing exactly the correct solution.
everyone was, every kid.
Yeah, every
kid.
kid in every geography class. Yeah.
So it wasn't like it was anything unusual, it just, we're all going, it fits, it's a puzzle.
Well, I took a trip to Alaska. Well, I've been there 3 or 4 times now, but one of the times I was on a plane flying over Mount McKinley, or Mount Denali, and there was some mountains off in the distance, and the guide who was with us that day said, those mountains cannot be explained. He said, the terrain, remember the geologic term terrain, the terrain associated with those mountains is most like a terrain, I think he said in New Zealand, and it shouldn't be here in the middle of Alaska, and they don't know why. And I believe that's likely true. I'm not sure how knowledgeable this person was about geology, but that sounds plausible to me. There are still mysteries. How did pieces of terrain get halfway around the world? There's still mysteries about what happened in detail during the breakup of some of these continents. Where did pieces go and why? It's amazing stuff.
Another comment that's been made is about Lake Agassiz, and that when it finally drained, it drained east, and that's what caused the Lesser Dryas.
Oh, yeah,
It
fascinating.
turned the oceans upside down.
Yeah,
essentially.
changed the salinity of the ocean. Yeah. It drained. It had a complex drainage pattern. It broke apart in regions. The ice dams broke apart
Yeah.
over thousands of years. And for a while, it drained into the Mississippi and through the Warren River in Minnesota. And then it started draining into the Hudson Bay, and sometimes it drained east. Dump all that fresh water into the ocean, and it changes the salinity. And so there's speculation that changed the thermohaline currents that drive the North Atlantic circulation, and might have slowed or turned off that circulation, which caused even though it was the end of an ice age and things were warming up, it plunged northern Europe into the Younger Dryas, a cold period. It's all interconnected. It's amazing.
And my final thought was, if you ever drive through eastern Washington, and you're coming out of Idaho and you're driving down towards the Pacific, you go through that wash basin area, and you look at it and you wonder, what the hell caused that?
Right.
This is impossible. And then you go, well, there's this big, huge lake up
Right.
there, and it just drained in a matter of a week or two or a month
Yeah.
at most. And you go, oh,
Thousands of Niagara Falls, hundreds
Just-
of thousands of Niagara Falls drained within periods of
but it's
weeks.
staggering to drive through
Yeah.
that area. The topography is mind-boggling, especially for people from either the Midwest, and by the way, we are sitting on top of a moraine, or the people like I am from the East Coast, that this is completely foreign. Now, it can't happen.
Right, amazing. This incredible stuff. Knowing our world is so exciting. Anybody else have any questions or comments? All right.
I thought it was interesting, the Mediterranean, the whole drainage, and usually that was, for much of its time, the Gibraltar was closed there, actually, and the whole, it was a sea that was completely closed, and it was somewhere a couple hundred feet below where it is now. And all the different things, caves, a lot of caves where people from Paleolithic times lived down, which is under the water right
Well,
now.
and not only that, the ice caps locked up so much. You're right. I mean, it's so much archaeology has been buried in the ocean because of the Mediterranean and the Caspian and the Black Sea and some of these other places that were inundated after the last ice age or significantly changed. But even the ocean. So there are caves around South Africa where you have to rappel down a cliff to get to these caves. But in Paleolithic times, when the ice sheets were covering the northern hemisphere, the water levels in the oceans were low enough that you could have walked up to these cliffs and then climbed up them instead of rappelling down them to these. And people live there. And there are places underwater around the shores of South Africa where some of the most ancient human habitations are thought to exist. But they're all underwater now because of rising sea levels that happened after the glaciation. It's all linked together.
Yeah, I think some of the interesting stuff too is, as they were finding out that continental drift was really occurring, you could see fossils that were exactly the same, and even geological structures that were same. But they could predict that, I think it was Darwin that predicted that they would find a certain type of tree in Antarctica, because it had been seen in South America and had been seen in Africa, and the whole compilation of that should show that to get there, to have that tree be there, and they did find those fossils in Antarctica.
Yeah, that's something I didn't have time to get into, but you've got things called index fossils and index strata, where you can match up the isotopes and the chemical composition between, say, the Atlas Mountains and the Appalachian Mountains to show that they are part of the same terrain, or were at one point.
Right.
And then index fossils share a similar role in helping us date and locate things.
Yeah.
All right.
Well, we could keep talking about this forever, and maybe we should go out to lunch and talk about it
All
some
right.
more.
Good idea. All right. Thanks, everybody. See you at the next exciting Science Sunday.
Anybody home wants to, I think we're going to Panera, right? Join us at Panera if you'd like.
All right.
Nice, fun.
That was great.
Ah,
But my husband is a geology nut.
oh, really?
So we're going to watch this again. Because we've been to some of the places you talked about.
Oh, great.
The Grand Staircase Escalante.